Stellar kinematics is the study of the movement of stars without needing to understand how they acquire their motion. This differs from stellar dynamics, which takes into account gravitational effects. The motion of a star relative to the Sun can provide useful information about the origin and age of a star, as well as the structure and evolution of the surrounding part of the Milky Way. In astronomy, it is widely accepted that most stars are born within molecular clouds known as stellar nurseries. The stars formed within such a cloud compose open clusters containing dozens to thousands of members. These clusters dissociate over time. Stars that separate themselves from the cluster's core are designated as members of the cluster's stellar association. If the remnant later drifts through the Milky Way as a coherent assemblage, then it is termed a moving group. Space velocity at the component of stellar motion toward or away from the Sun, known as radial velocity, can be measured from the spectrum shift caused by the Doppler effect. The transverse, or proper motion must be found by taking a series of positional determinations against more distant objects. Once the distance to a star is determined through astrometric means such as parallax, the space velocity can be computed. This is the star's actual motion relative to the Sun at the local standard of rest, LSR. The latter is typically taken as a position at the Sun's present location that is following a circular orbit around the galactic center at the mean velocity of those nearby stars with low velocity dispersion. The Sun's motion with respect to the LSR is called the peculiar solar motion. The components of space velocity in the Milky Way's galactic coordinate system are usually designated u, v, and w, given in km per second, with u positive in the direction of the galactic center, v positive in the direction of galactic rotation, and w positive in the direction of the north galactic pole. The peculiar motion of the Sun with respect to the LSI is u, v, w, equals 11.1, 12.24, 7.25 km per second, with statistical uncertainty, plus 0.69 minus 0.75, plus 0.47 minus 0.47, plus 0.37 minus 0.36 km per second, and systematic uncertainty 1, 2, 0.5 km per second. Note that V is 7 km per second larger than estimated in 1999 by Denon et al. The stars in the Milky Way can be subdivided into two general populations, based on their metallicity, or proportion of elements with atomic numbers higher than helium. Among nearby stars, it has been found that population I, higher metallicity stars have generally lower velocities than older population II stars. The latter have elliptical orbits that are inclined to the plane of the Milky Way. Comparison of the kinematics of nearby stars has also led to the identification of stellar associations. These are most likely groups of stars that share a common point of origin in giant molecular clouds. Within the Milky Way, there are three primary components of stellar kinematics: the disk, halo and bulge bar. These kinematic groups are closely related to the stellar populations in the Milky Way, forming a strong correlation between the motion and chemical composition, thus indicating different formation mechanisms. The halo may be further subdivided into an inner and outer halo, with the inner halo having a net prograde motion with respect to the Milky Way and the outer a net retrograde motion. High-velocity star SIDAT. Depending on the definition, a high-velocity star is a star moving faster than 65 km per second to 100 km per second relative to the average motion of the stars in the Sun's neighborhood. The velocity is also sometimes defined as supersonic relative to the surrounding interstellar medium. The three types of high-velocity stars are Runaway stars, halo stars and hypervelocity stars. Runaway starset. A runaway star is one that is moving through space with an abnormally high velocity relative to the surrounding interstellar medium. The proper motion of a runaway star often points exactly away from a stellar association, of which the star was formerly a member, before it was hurled out. Two possible mechanisms may give rise to a runaway star. In the first scenario, a close encounter between two binary systems may result in the disruption of both systems, with some of the stars being ejected at high velocities. In the second scenario, a supernova explosion in a multiple star system can result in the remaining components moving away at high speed. Although both mechanisms are possible, astronomers generally favor the supernova mechanism as more common in practice. One example of a related set of runaway stars is the case of Aurorigae 53 Arietis and Mu Columbae, all of which are moving away from each other at velocities of over 100 km per second. For comparison, the Sun moves through the Milky Way at about 20 km per second faster than the local average. Tracing their motions back, their paths intersect near to the Orion Nebula about 2 million years ago. Barnard's Loop is believed to be the remnant of the supernova that launched the other stars. Another example is the X-ray object Vela X1, where photodigital techniques reveal the presence of a typical supersonic bow-shock hyperbola. Halo starset. High-velocity stars are very old stars that do not share the motion of the Sun or most other stars in the solar neighborhood, which are in similar circular orbits around the center of the Milky Way. Rather, they travel in elliptical orbits, which often take them well outside the plane of the Milky Way. Although their orbital velocities in the Milky Way may be no faster than the Sun's, their different paths result in the high relative velocities. Typical examples are the halo stars passing through the disk of the Milky Way at steep angles. One of the nearest 45 stars, called Captain's star, is an example of the high-velocity stars that lie near the Sun. Its observed radial velocity is -245 km per second, and the components of its space velocity are u equals 19 km per second, v equals -288 km per second, and w equals -52 km per second. Hypervelocity starset. Hypervelocity stars, designated as HVS or HV in stellar catalogs, are stars with velocities that are substantially different from that expected for a star belonging to the normal distribution of stars in a galaxy. Such stars may have velocities so great that they exceed the escape velocity of the galaxy. Ordinary stars in the Milky Way have velocities on the order of 100 km per second, whereas hypervelocity stars, especially those near the center of the Milky Way, which is where most are thought to be produced, have velocities on the order of 1,000 km per second. The existence of HVSs was first predicted by Jack G. Hills in 1988, and their existence confirmed by Warren Brown, Margaret Geller, Scott Kenyon, and Michael Kurtz in 2005. As of 2008, 10 unbound HVSs were known, one of which was believed to have originated from the Large Magellanic Cloud rather than the Milky Way. Further measurements placed its origin within the Milky Way. Due to uncertainty about the mass distribution within the Milky Way, determining whether a HVS is unbound is difficult. 5 additional known high-velocity stars may be unbound from the Milky Way and 16 HVSs are thought to be bound. The nearest currently known HVS, HVS2, is about 19 kpc from the Sun. It is believed that about 1,000 HVSs exist in the Milky Way. Considering that there are around 100 billion stars in the Milky Way, this is a minuscule fraction, approximately 0.00001%, equals origin of hypervelocity stars equals HVSs are believed to originate by close encounters of binary stars with the supermassive black hole in the center of the Milky Way. One of the two partners is captured by the black hole, whereas the other escapes with high velocity. Also, captured does not necessarily mean swallowed, as the companion to the HVS may enter an orbit around the black hole. However, this can only happen if the binary stars are falling nearly directly toward the black hole from extremely far. Otherwise the speed gain would not be sufficiently high. Supernova-induced HVSs may also be possible, although they are presumably rare. In this scenario, a HVS is ejected from a close binary system as a result of the companion star undergoing a supernova explosion. Ejection velocities up to 770 km per second, as measured from the galactic rest frame, are possible for late-type B stars. This mechanism can explain the origin of HVSs which are ejected from the galactic disk. Known HVSs are main-sequence stars with masses a few times that of the Sun. HVSs with smaller masses are also expected, and K-dwarf HVS candidates have been found. It has been suggested that the HVSs in the Milky Way are a result of the passage of an orbiting dwarf galaxy near the Milky Way. When the dwarf galaxy made its closest approach to the center of the Milky Way, it underwent intense gravitational tugs. These tugs boosted the energy of some of its stars so much that they broke free of the dwarf galaxy entirely and were thrown into space. Due to the slingshot-like effect of the boost, some neutron stars are inferred to be traveling with similar speeds. This could be related to HVSs and the HVS ejection mechanism. Neutron stars are the remnants of supernova explosions, and their extreme speeds are very likely the result of an asymmetric supernova explosion or the loss of their near partner during the supernova explosions that forms them. The neutron star RxJ0822-4300, which was measured to move at a record speed of over 1,500 km per second, 0.5% c. in 2007 by the Chandra X-ray Observatory, is thought to have been produced the first way. Some kind of supernovas are expected to happen if a white dwarf collides with its nearby partner and consumes the outer matter of this partner. The white dwarf and its nearby partner have very high orbital velocities at this time. The huge mass lost of the white dwarf during the supernova causes the nearby partner to leave at its previous huge orbital speed of several hundred kilometers per second as a hypervelocity star. The supernova remnant of the exploding white dwarf leaves because of its own high orbital speed as a new fast-traveling neutron star. This seems to be the most likely origin of most HVSs and fast-traveling neutron stars. Partial list of HVSs edit equals. As of 2014, 20 HVS were known. HVS 1. SDSSJ090744.99 plus 024506.8. A. The outcast star. The first hypervelocity star to be discovered. HVS 2. SDSSJ093320.86 plus 441,705.4. Or US 708. HVS 3. He 04375439. Possibly from the Large Magellanic Cloud. HVS 4. SDSSJ091301.00 plus 305,120.0. HVS 5. SDSSJ091759.42 plus 672,238.7. HVS 6. SDSSJ110557.45 plus 09343.9.5. HVS 7. SDSS-J113312.12 plus 010824.9. HVS8. SDSS-J094214.04 plus 200,322.1. HVS9. SDSS-J102137.08 005234.8. HVS10. SDSS-J120337.85 plus 180,250.4. TYC88401782-1. Kinematic groups. Edit. A set of stars with similar space motion and ages is known as a kinematic group. These are stars that could share a common origin, such as the evaporation of an open cluster, the remains of a star-forming region, or collections of overlapping star formation bursts at differing time periods in adjacent regions. Most stars are born within molecular clouds known as stellar nurseries. The stars formed within such a cloud compose gravitationally bound open clusters containing dozens to thousands of members with similar ages and compositions. These clusters dissociate with time. Groups of young stars that escape a cluster, or are no longer bound to each other, form stellar associations. As these stars age and disperse, their association is no longer readily apparent and they become moving groups of stars. Astronomers are able to determine if stars are members of a kinematic group because they share the same age, metallicity, and kinematics, radial velocity and proper motion, as the stars in a moving group formed in proximity and at nearly the same time from the same gas cloud, although later disrupted by tidal forces. They share similar characteristics. Stellar association. SDT. A stellar association is a very loose star cluster, whose stars share a common origin, but have become gravitationally unbound and are still moving together through space. Associations are primarily identified by their common movement vectors and ages. Identification by chemical composition is also used to factor in association memberships. Stellar associations were first discovered by the Armenian astronomer Victor Ambartsumian in 1947. The conventional name for an association uses the names or abbreviations of the constellation, or constellations, in which they are located, the association type, and, sometimes, a numerical identifier, equals type. SDT equals. Victor Ambartsumian first categorized stellar associations into two groups, OB and T, based on the properties of their stars. A third category, R, was later suggested by Sidney van den Berg for associations that illuminate reflection nebulae. The OB, T, and R associations form a continuum of young stellar groupings, but it is currently uncertain whether they are in evolutionary sequence, or represent some other factor at work. Some groups also display properties of both OB and TU associations, so the categorization is not always clear-cut. OB association. SDT equals. Young associations will contain 10 to 100 massive stars of spectral class O and B, and are known as OB associations. In addition, these associations also contain hundreds of thousands of low and intermediate mass stars. Association members are believed to form within the same small volume inside a giant molecular cloud. Once the surrounding dust and gas is blown away, the remaining stars become unbound and begin to drift apart. It is believed that the majority of all stars in the Milky Way were formed in OB associations. O-class stars are short-lived, and will expire as supernovae after roughly 1 million years. As a result, OB associations are generally only a few million years in age or less. The OB stars in the association will have burned all their fuel within 10 million years. Compare this to the current age of the Sun at about 5 billion years. The Hippocos satellite provided measurements that located a dozen OB associations within 650 parsecs of the Sun. The nearest OB association is the Scorpius-Centaurus association, located about 400 light-years from the Sun. OB associations have also been found in the Large Magellanic Cloud in the Andromeda Galaxy. These associations can be quite sparse, spanning 1,500 light-years in diameter. T association equals. Young stellar groups can contain a number of infant T Tauri stars that are still in the process of entering the main sequence. These sparse populations of up to 1,000 T Tauri stars are known as T associations. The nearest example is the Taurus Auriga T association, Tau Aur T association, located at a distance of 140 parsecs from the Sun. Other examples of T associations include the Arcorona Australis T association, the Lupus T association, the Chameleon T association, and the Velorum T association. T associations are often found in the vicinity of the molecular cloud from which they formed. Some, but not all, include OB-class stars. Group members have the same age and origin, the same chemical composition, and the same amplitude and direction in the vector of velocity. R association equals. Associations of stars that illuminate reflection nebulae are called R associations, a name suggested by Sidney van den Berg after he discovered that the stars in these nebulae had a non-uniform distribution. These young stellar groupings contain main sequence stars that are not sufficiently massive to disperse the interstellar clouds in which they formed. This allows the properties of the surrounding dark cloud to be examined by astronomers. Because R associations are more plentiful than OB associations, they can be used to trace out the structure of the galactic spiral arms. An example of an R association is Monoceros R2, located 830 plus or minus 50 parsecs from the Sun. Moving groups. If the remnants of a stellar association drift through the Milky Way as a somewhat coherent assemblage, then they are termed a moving group, a kinematic group. Moving groups can be old, such as the HR 1614 moving group at 2 billion years, or young, such as the AB Dor moving group at only 120 million years. Moving groups were studied intensely by Olenegan in the 1960s. A list of the nearest young moving groups has been compiled by Lopez Santiago al. The closest is the Ursa Major moving group, which includes all of the stars in the Plough, Big Dipper asterism except for Alpha Ursae Majoris and Eta Ursae Majoris. This is sufficiently close that the Sun lies in its outer fringes, without being part of the group. Hence, although members are concentrated at declinations near 60 degrees north, some outliers are as far away across the sky as Triangulum Austral at 70 degrees south. Stellar streams. A stellar stream is an association of stars orbiting a galaxy that was once a globular cluster or dwarf galaxy that has now been torn apart and stretched out along its orbit by tidal forces. Known kinematic groups. Some kinematic groups include, see also astrometry, Gaia probe, Hippocos, N-body problem, open cluster remnant. Further reading. Majewski, Stephen R. 2006. Stellar Motions. University of Virginia. Retrieved 25 February 2008. The Space Velocity and Its Components. University of Tennessee. Retrieved 25 February 2008. Blayoff A. Morgan W. 1954. The Space Motions of Aurora and Mu Columbae with respect to the Orion Nebula. Astrophysical Journal. V. 119. p. 625. Hugewer Far. De Bruijn J. H. J. Desiu P. T. 2000. The Origin of Runaway Stars. Astrophysical Journal. V. 544. p. L. 133. Brown, Geller, Kenyon, Kurt. 2006. A successful targeted search for hypervelocity stars. Astrophysics. J. 640. 35. Arcs of AstroPH 0601580. Bibcode 2006 APJ 640L 35B. DOI 10.1086 503,279. Edelman, H. Napiwatsky, R. Heber, U. Kreislieb, N. al. 2005. He 04375439. An unbound hypervelocity main sequence B-type star. The Astrophysical Journal. 634. 2. L181L184. Arcs of AstroPH 0511321. Bibcode 2005 APJ 634L 181E. DOI 10.1086 498,940. Edit. ESO press release about runaway stars. Entry in the Encyclopedia of Astrobiology, Astronomy, and Spaceflight. 2 exiled stars are leaving our galaxy forever. Entry in the Encyclopedia of Astrobiology, Astronomy, and Spaceflight. Hypervelocity stars. I. The spectroscopic survey information on HV6 and HV7. Young stellar kinematic groups. David Montes. Departamento de Astrofísica. Universidad Complutense de Madrid.